Okay, what's up? Happy Thursday, everybody. Yeah, let's see. So I still have COVID, which is still awesome, but I've got kind of the rest of the stuff for our motion estimation stuff ready to go through. Couple quick announcements. So I've updated Project 3. So kind of the first part, which is focused on Flan. Hasn't really changed all this stuff with Kirby. And then for one of the applications, so for one of the second parts you can choose from, I've put one up for motion estimation and in particular fine motion estimation. So you can go out there and you can take a look at that and see kind of the second half of Project 3 if this is the topic you're interested in want to pursue. So those are up. Like I said, due date's May 7th. So everything's up and running fine on my end. So I'm going to go ahead and share my screen. Here we go. So hopefully everyone can see the slides. And I'm just going to pick up where we left off last time. So we were talking about types of motion, motion estimation. And we sort of talked, we've got rigid and non-rigid. Does it deform? Does it not deform? We talked about local versus global. So is the entire camera moving, right? Is the entire scene moving, or is just some object inside the scene moving? And we said we can look at it, a couple different ways. We said we had four models. One was just everything's in a straight line. All we care about is delta X and delta Y. One is, okay, we care about delta X and delta Y, and now we'll care about rotations and Euclidean. We've got, your old friend theta shows up. And then there's affine, which is the 6 parameter model, which is what we discussed last time, which is essentially a really fancy combination of translational and Euclidean motion models. And then the last one is homographic projection, which we talked about with image stitching, which is a whole heap and heap and heap of linear algebra. So we're not going to do anything with homographic projection for this, but if you go out and you look at applications, one of the things you'll see a lot in that area is optical flow is one of the models in that area you see a lot that people like. But if you want to go out there and learn more about it, you can. It's just a lot of really complicated matrix stuff that is more accurate than anything we need for a class like this. So we talked about our affine motion estimation and our assumptions we're making. And those assumptions were that whatever is moving at a constant rate. Pixels are discrete, images are discrete. There's no such thing as a continuous function that will join two pixels. They exist wholly of themselves. So we also have to assume velocity is constant. We're not working on things that accelerate. And we are not working with things that are moving in and out of the foreground and the background. In general, making this assumption that the intensity or the brightness in the color space or the HSI space is the same. So what we're looking at isn't getting brighter or darker. And we also looked at how with a fine motion estimation, you need to be tracking relatively large objects inside the scene because of fine motion is very sensitive to blur and noise. And you can see that with a lot of kind of the motion blurring if you're swinging your camera around really fast in an FPS game. Less so now because graphics cards are really good, but if you're old like me, you've seen it. And so if you're looking at little things, it's really hard. And it's kind of the flip side of feature detection and matching and extraction, where having a blurry image is good because it slows down gradient descents and helps us find them easier. In motion control, blurriness is a bad thing because we're already working with estimations with the models we use. So adding noise makes the estimation even more estimation. And we talked about the first way of doing motion estimation within a fine motion model. And that was with block matching. And block matching is more or less what it sounds like. We are subdividing the image into blocks. We talked about it. They're usually a function of 8. I think that's for a different class. Yeah. Okay. Sorry about that. I thought maybe someone hopped on the Discord. Okay, so we're doing block matching, which is, like I said, we subdivide the image into blocks because of sort of the way things are stored and the history of how we've worked with things. The size of the block is typically going to be either 8, 16, or 32 by 32. And it's just, one of those holdovers from the way stuff is stored and the way graphics cards worked on board. Or video game consoles. Hang on, I forgot to take my Dayquil. All right. And the way we do it is we take our block in the first frame and we figure out how it's moving with our 6-parameter model. And then we move on to the next frame and we compare frame 1 to every block in frame 2, find the one that matches, and then say, all right, well, block in frame 1 move to this position in frame 2. And you can kind of see that with these images where I've got this red ball is moving from left to right. And so in the first image, I have my block that has the ball in it. And so in my second image, I search every block until I find the block with the ball in it. And then in my third image, I search every block until I find the block with the ball in it again. And we track motion as a function of how these blocks are moving, which is why it's sensitive to noise. It's why it doesn't work great with blurry images, because it's a very sort of gross scale measure of comparison. You're dealing with, if you have a 32 by 32 square, that's a lot of pixels to be trying to keep up with to try and match in the next frame. So the thing with a fine motion estimation, the way it sort of works is we are preserving the features from frame to frame. And what that means is when we figure out how things are moving, we want them to be moving in a way that keeps our points, our lines, and our planes the same from frame to frame. And so, like I said, we make our blocks in the first image, we look for our blocks in the second image, we look for our blocks from the second image to the third image, and so on and so forth until eventually we back out this 2D motion model where we find A1, we find A2, and we find TXTY, and then we can just plug in whatever XY we're looking for and figure out how it's moving. So that is with block search, which is terrible. So the much, much, much better way to do this is with features, right? We've spent a whole semester figuring out how to find, extract, and match features, and so now we get to actually do something with that information. And motion estimation using features, like I said, is much, much better and much, much faster. So instead of seeing how a block moves, we want to see how a key point moves or a feature vector moves, right? So what we can do is we can just use our model, SIFT or SURF, or orb typically, since we can't use SURF. But we want to use that, and then we want to use FLAN to match our key points. And then we just look for those same key points in the second frame. And we say, key point 1 move to this position in frame 2, and then it moved to this position in frame 3. And we can much easier and faster back out how those key points are moving. Because in this instance, it's actually very straightforward. You can just use some, clever kind of Newtonian mechanics, because this key point is moving across the scene. And all you really care about is its location, instead of trying to figure out how a whole block of things are moving. And so this, like I said, this is much easier. We just want to pull out our key points, and then we want to look for those key points in each subsequent frame. And so you can kind of see, here's what a fine motion estimation looks like if we're using features, which is where we've got our source image, our red ball, and we're going to find our feature vector for a red ball. We're going to find all our feature vectors in the image. We're going to find out which one is the red ball. And then we're just going to find that key point in every subsequent frame and use its motion through those frames to find its motion equation in motion. So kind of setting it up with a block search is a little misleading, because it's just such a worse way of doing it. But it's important to kind of see the general concept where, I want to find what happened to this stuff in frame 1 to get it to the place it is at in frame 2. I was able to put a demo of this together. So I'm going to switch over to this notebook. All right, so we're going to take a look at just our simple images with the tree and the ball, and looking at creating an affine motion model. So our first way we're going to do it is we're going to look at 2 frames of tree and ball, and we're going to do a block search. So what you can see in the code is we load in our images, we create our blocks, right? You can see here our blocks are 32, so 32 by 32 pixels. We make our blocks, we do a search. Here we put them somewhere. Then we do our big gross for loop to look at all the other blocks. And then based off of that, here are our parameters we want to find. And we do a bunch of stuff, and then we visualize it. And I'm actually going to start so we can see this running. So we do our block matching, we do our affine transformation, and what you can see here is our A11, A12, A21, A22, T1, and T2. So for any X or Y we want to know the position of, we can just multiply X and Y by our transformation matrix, and that will tell us where we are. And you can see here, it's done a little bit of estimated motion vectors. And what we're going to see is, if we look at the transformation, the ball hasn't moved. It's actually flipped this kind of this way, right? So what's happened here is, when I just gave it a block search and some frames, OpenCV assumed I meant I want to know how the global image is moving. It assumed everything was moving, not just that red ball. So you can see, when we have our 2 real images where the ball's close to the tree and then the ball's farther from the tree, in order for the ball to move away from the tree, if we assume everything's moving, then that means everything has to be going this way. So that is what has caused this. You can see we've got kind of all these velocity vectors saying everything in the image is tilting this way to accommodate this ball going this way because I think everything is moving. And that's how we end up with this. So right away we tried, block matching, and that's the thing in particular with block matching is that it is good for global motion estimation. It is terrible for object motion estimation. If you want to know how something in the scene is moving, just one thing, you need to first, define what that thing is with some numbers, and then you can do your motion estimation, with your object numbers instead of just your whole global scene. So what we want to do now is, let's do this again, but we'll do it with key points. So we just sort of have this extra step now where before wanted to create our blocks, here we want to create our key points. So we find all of our key points, then we go in and match our key points, and then we come up with our equation of motion, and now we have all right. So clearly this looks much, much better. We found all the key points in the tree. We figured out that none of those key points are moving, right? The tree isn't going anywhere. So you can still see there's some tiny little velocity vectors up there in the leaves that is just, we're not getting as good a results as maybe we could have because it's not a great image and we didn't do any tuning. But overall, we can very clearly see that the key points that define the ball have moved. And we know that this now becomes the equation of motion for the red ball. So by feature matching, we were able to do this much, much better. And like I said, we were able to only look at the one thing we cared about. So what we can do is once we have our equations of motion, we can start predicting where that object is going to be in future frames. So if I were to say, I'm going to take another picture after this one, and the ball's motion is going to stay the same, then I can just use my transformation matrix, my affine model, to tell me where it should be. And we can do that here where I want to know where is the ball going to be in the third frame if I calculate it with my affine motion equations, or if I calculate it just by looking at the third frame. So what this is here we have at the bottom, I said I gave it the equation of motion we got right here. Let's see if we can, yeah. So we took this affine transformation, and this little bit of code says use this information and the starting point in frame 1 to tell me where the ball will be in frame 3, right? And this is where the ball is in frame 3, and this is where my affine motion model told me the ball would be in frame 3. So a lot of the math behind it with the matrices and whatnot, like I said, we didn't get into, we're not going to get into. That's more of like a graduate linear algebra type of deal. But the main takeaway really is we can estimate motion so we can figure out how something is moving in an image. We have some nice tools to help us do that. And those tools are based on our ability to find key points, essentially. If we really wanted to do motion estimation, real, with a real sort of setting and purpose, this is how we would do it. We would first kind of want to go through everything we learned this semester to get to the point of having really good key points for the thing you care about in the image. And then for the application, we can, use some nice built-in types of functions with SIFT and our key points and all the fun stuff we've learned. And if we have good key points, we can, at that point, essentially ask the math to give us an equation of motion, which is what we have here. So that is it for motion estimation. This is on my courses. I don't know if I've pushed it to the Git repo yet, but I will when class is over. What I want to do now is, I'm going to stop sharing for a second. To pull up the next half of motion estimation and moving stuff around in computer vision and sharing the screen again. Oh, okay, there's some questions. Yeah, there's no more Pikachu in the homework. And looking for more than one block, that's a good question because that's what makes block search suck for object tracking. Because it doesn't want to look for more than one block. And if we ask it to look for more than one block, we're essentially just asking it to look for bigger blocks. And so then we get more noise and then we have a harder time finding what we care about. So it's really only good for global motion estimation. And it is good at that in that it will save you a little bit of time because you don't have to do any feature matching beforehand. But if you are tracking features, you can't really use it. And, that's why, because you can see in the slide, if the ball is overlapping two different blocks, unless there's just enough of the ball in one block, it's not going to see it. And unless there's just not enough of the other block, it's going to put it in that block. So that's the other thing, is a block search is really kind of just a binary. There's going to be some sort of threshold where it's going to decide which block it is in, and either decision will be poor. And I will actually, let me share my screen. Screen one, here I will pull the project 3 stuff. So all of the Kirby stuff is the same, right? You still want to do all of that with Flan. There's no more Pikachu or YOLO. Like I said, I was out of my mind when I thought I could teach YOLO in a couple of days at a 400 level class, so that's my bad. Instead, we are going to have a part about motion estimation. And so basically, I just have dumped 2 GIFs up there. So one is Homer disappearing into the bush, and you guys are going to use kind of the 2 different methods to see if you can figure out the equation of motion for Homer. And then based off of that equation of motion, you're going to take the inverse and see if you can basically turn it into a GIF of Homer walking out of the bushes instead of into the bushes. Minimum amount of features. It's just what you put in the code. However you say this block equals this block, and whatever threshold you give it or whatever size you give it. It's just going to depend on that. So I would say if there were a minimum amount of features, it would really depend on the size of the block. If you were using a big size block, say 32 by 32, then you would need to have more features in there to try and find. And if it was like an 8 by 8 block, you would really only want it to find like one feature. Do you know what I mean? So I guess it fluctuates based off of how you set up the search. So I've got Homer for local motion. And I will say, going into this, part of the assignment is to do this to estimate Homer's motion with block matching. I'll just go ahead and tell you right now, it's not going to work. It's, an exercise I want you guys to go through to see kind of the concept of block matching and why it's not going to work. And so when you do the assignment, if it looks like crap, it's supposed to. So heads up. But so you're going to do block matching and feature matching for this, and it'll give you a chance to see what it looks like if something's moving in local space. And then the second part of the problem is a gift from Incantation, which if anyone likes horror movies and has not seen Incantation, it is absolutely goated and terrifying. But it's a found footage horror film. So the camera is moving in this case and not anything inside of the picture. So this is a global motion problem. And so while you're doing a local motion problem with Homer, this is going to be a global motion problem where you want to figure out how the camera is moving as it moves through kind of the things it's looking at. So, and with this one, you'll probably find block search where it's a lot better, especially when what is in the image changes, right? You can see it switches from the front facing view where you see the protagonist's face about to get eaten by demons or whatever, and then they flip the camera around and you can see the spooky lady staring at the wall. And if you ever wanted to know what Professor Durst does with his free time, it's almost exclusively drink and watch horror movies, with the occasional break to watch monster movies. If anyone wants to know any insanely random trivia about Godzilla, just let me know. Okay, so that's the new second part of Project 3. If you want to do motion estimation, is basically a local motion estimation problem and a global local estimation problem, both done with block search and then with feature matching. So next, kind of on the rung of applications as we kind of continue our conversation about motion estimation, is structure from motion. So the idea is we want to find a 3D geometry using 2D images, right? And so this is here, we talked about this. This is how we're moving. These are our motion models, okay? When we want to do structure from motion, we want to break this down so our structure is 3D points in space. It is a point cloud is what it's usually called, but it's essentially just an array of space of XYZ points of where everything is in the world. So our structure is a physical location in the world in 3 dimensions. Our motion is that the camera is moving over time because we can only find structure if we have some frame of reference, some baseline, some sort of standard to which we can kind of compare, and that will help us out. There are some monocular structure for motion algorithms. I'm not going to talk about them because there's a lot of lift in terms of parameters and assumptions and constraints. So we're not going to worry about monocular structure for motion. But the idea is if we have a set of 2D images that have been taken by a moving camera or eyeball, we want some way of turning an array of pixels in their image space. So we have an array of RGB values, or we have an array of HSI values, or whatever image space we're working in. We have this two-dimensional array full of image space pixels. And it's our job with structure for motion to find a way of turning our pixels in image space to points in world space. Right? We're going from sort of our abstracted color space, feature space, scale space, whatever. And we need to math our way through that to get us to reality, essentially. And so how are we going to do that? How do we get there, right? Like, how do we go from 2D to 3D, and we start from this kind of simple fact that an image is two-dimensional. I mean, there's just full stop, an image is a two-dimensional projection of the world. It is pixels located inside of the image. The thing is that those pixels in the image do correspond to a thing that exists in 3D space. So whenever we look at stuff, whenever we look at an image, whenever we look at a monitor, we're essentially just looking at a two-dimensional projection of the world onto some sort of imaging surface. And so that includes us, right? When we see something, it is displayed on our visioning plane. I don't remember the name, but the back of the lens where our eyeball is it's mostly flat, but it's made out of right here, right? Your vision plane is kind of a flattish surface of flesh goop upon which your retina and lens focus light. So you essentially have a 2D surface of photoreceptors that take all the light into it. And if you're doing a camera, right, instead of sort of our flesh goop, it's a 2D electrical goop, usually a charge coupled device, which is just an array of little diodes that will turn in energy from a light into an electrical signal, which is very much what our eyes do. In both cases, it is the overlap of the two-dimensional images that gives us three-dimensional space. Like, we understand depth essentially because of stereoscopic vision, because we have two eyeballs and they point forward because we're predators and we need to see really well in front of us instead of okay everywhere around us. And so that's how it works. Humans are essentially just walking structure for motion eyeballs attached to a person. And the idea of stereo vision is you have these two overlapping images, and you can find the relative position in each image, smoosh that together, and it will tell you essentially how far away from you it is, which is why, if you guys watch Futurama and Leela and the Cyclops, or any sort of gag in media where you have a person with one eye that has no depth perception, and it's because without two sort of images to overlay, you do in fact have no depth perception. So the way we get from 2D images to a 3D world is through stereo vision. And like I said, it's two overlapping images. And the distance between those is called parallax. So you can think of parallax as the amount of overlap between the two images. Or another way to look at it is it's really a measure of how far apart from each other either the eyeballs or the cameras are. And so the further apart they are, you have a much narrower strip of overlap kind of at the very edges. And that is good for seeing things that are far away. As you increase parallax and you increase distance, your far field of view gets better, and you can see things farther away with more clarity, much more so than things that are close to you. Which again is, if you have a prey animal, their eyeballs are usually quite far apart, so they can have a very large field of view of very far away things. As you kind of push the eyeballs together, or if you push your two cameras together, you lower the parallax, so you increase the amount of overlap between the two images, which gives you much better near field vision. So there's always this trade-off when you're designing a computer vision system for structure from motion, where you kind of have to decide based on your application how much parallax you need, right? How far apart or how close do I have to put the cameras to increase or decrease the amount of overlap between the two images when I go to solve for 3D geometry. So the steps from structure from motion, we skip any amount of block matching, blah, 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 and jump straight to feature matching. Unlike motion estimation, where we're wanting to see how certain key points move, in structure from motion, we want to see how every key point moves. So it's the feature extraction part, but there isn't a feature matching part. So that is what is different about structure from motion. Structure from motion, we want to see every feature, which is different from basically everything we've done until now. So what we do is we find our features, we pick them out, we find those key points in each image, and if I know where a key point is in image 1, and I know where that same key point is in image 2, or if I know where it is in the left image and I know where it is in the right image, I can do a bunch of matrix multiplication to find out where that key point is in 3D space. And we do that with what's called pair reconstruction, where we start from our two images, we find all the key points in each image, and then the math we do to basically say if key point is here on the left and here on the right. I'm not going to go into the math of this, but just so you know the words, if you keep working with structure for motion in your life, it's done using what's called epipolar geometry. And to do kind of the simple version, for an image, the very center of the image, kind of the middle pixel, that's called the epipole, and it's literally just the middle of the image. And then you have your epipolar line, which is the line between the key point and the center of the image. And then you overlay the two epipoles because the constraint is such that the epipolar line will be preserved between right and left images. So that means the line itself, not its physical location, right? You can think of it like the slope of a line in two images. That key point has to fall upon the epipolar line regardless of which image it is in. And so you can look at the key point's position relative to the epipole in both images and throw all of your math at that, and that will give you your XYZ point in physical space of that key point. And so what you do after that is what's called triangulation, which is a fairly common term. It means something a little different here. And the thing to note about structure from motion and stereo vision is you have to have a baseline pose. You have to turn on your stereo pair, your structure from motion cameras. You have to turn those on and let them think for a few frames to figure out where everything is and figure out kind of their epipole and the overlap between them. And then you can sort of turn it on and go. And the idea is, you start from your anchor where you know where stuff is, and you look at how key points move with relation to each image and to the baseline you started. That baseline of the initial triangulation, sometimes called an anchor. And essentially, you just have some function of the rotation translation, which is just a fancy way of saying the equation of motion for the camera relative to this point in space. And then you have the equation of motion for the other camera relative to that point in space. And you do your epipolar geometry, and you get back your XYZ coordinates. And then there's boatloads of post-processing you could do. Ransack shows up like it does for everything after you hit Flan and beyond, and some other stuff. I didn't put any code together for this for structure for motion just because this is a point at which you would really just want someone else's code. Quite frankly, if you want to look at structure for motion, the easiest thing is to find a good GitHub repo someone has made. There's boatloads of them. I'll post some as I come across them. I'm putting some more stuff together. But I just wanted to, since we were doing motion estimation, kind of tack on the idea of structure for motion and how we go from, how we go from finding key points in an image to understanding how features in the image are moving to fully understanding and collecting data about the real world and the real geometry of these things as they are moving. So that is all I had for today. The last thing we're going to talk about is facial recognition, which is going to be more in line with the SIFT and the orb and the flan stuff. It's really more about finding key points that are a part of a person's face, and then finding kind of key point motion in ways that faces kind of move. So it's not 3D or not kind of at the base level. It's more of a fun application of key point matching and flan. So that's the last thing we're going to talk about. I'll get some stuff together for next week, and then we'll just sort of work through project 3 and get everything wrapped up for the end of the semester. So awesome. Thanks for hopping on, everybody. And hit me up if you need me. If not, have a great weekend. Later.
Thank you, Professor.
Hey.